So in 8.2, we're going to take a look at distributions for sample proportions rather than sample means. Now, when we do this, we need to introduce some new notation. It's probably my favorite stats name if I had to pick one. This notation for the sample proportion is a p with this little caret symbol above it, and we read that as p hat. Quite literally just the idea of p wearing a hat on its head, right? So p hat is this symbol, the notation we use when we're referring to the proportion from a sample. And so what we want to look at here is the same idea that we looked at with the means. If we were looking at a small sample, right? You take a very small sample to represent something. So here we've got a poll conducted that says 42% surveyed believe the zombie apocalypse will occur. Well, let's look at the sampling distribution of the sample proportion for sizes, for samples of different size. So if that's the known proportion, right, percentage of the group that believe this. Well, if we surveyed 10 people and we did that 300 different times, and we look at each proportion that we got, each p hat that we get from each of those samples. Well, 42% is the actual percentage that's there. Obviously, some groups are going to have fewer people who believe, and some groups will have more people that believe. But we expect most groups to be around that particular value, or near the 42%. So you notice with these groups, the 300 samples of size 10, we would say there's a potential distribution for those proportions that we're getting from the 300 different samples. But if we increase that sample size so that every sample now includes 50 people, notice just like with the dice, it's much tougher. In fact, it's almost impossible to get 50 people where no one believes the zombie apocalypse will occur or everyone believes it will occur, right? The average, some do, some don't, the proportions start falling closer to that 42%, right? You notice they're kind of centered around roughly 40%. And then if we bump that up even more, if we're taking samples of size 100 and we do that 300 times, now we're really zooming in on just having these proportions that we get from our samples that are right around, located very near that 42%. So this idea kind of mimics the central limit theorem that we had as we increased our sample size. But there's a bit of a different rule to it for proportions. Now, first of all, I will mention one small detail that we need to have kind of hold true. Now, it will hold true for any of the problems we see in this chapter. But we want our sample size, we want it to be big, but we want it to still be smaller than 5% of the actual population size. Right? We don't want our samples to be too much of a part of the population. It kind of almost defeats the purpose at that point. So we won't really ever check this, but this is just a rule in play. The one we will check, and it's different from the central limit theorem of n being 30 or bigger, is this check right here. And this is saying that we need our sample size times that population proportion. P represents population proportion. Notice this is not p hat. So the sample size that we're taking times p times its complement, right? 1 minus p. We need that value to be at least 10. Again, just kind of this magic number that was determined statistically to allow any distribution of proportions that fits this criteria. We're going to say it gets that bell-shaped curve that we saw on the previous page. We're going to say that we can actually model the proportions distribution with the normal bell-shaped curve, as long as that sample size is big enough in comparison to what our values of P are that we're actually working with, okay? Now, with that distribution, we have a mean and a standard deviation, much like we had for X bar in 8.1. These are their individual formulas. Here is the formula all put together with our z-score formula. Because remember, again, z-score comes from value minus mean over standard deviation. I'll keep reminding you of that general idea, because now our value will be a question about a p hat, about a sample proportion. Our mean will be the actual proportion itself, and the standard deviation will be this huge square root calculation there in the denominator. So this will be our z-score formula for any of these questions involving proportions. So let's take a look at what those problems will look like. So we have, according to the CDCP, 18.8% of school-aged children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11, what's the probability that at least 19% are overweight? Notice when you read this question, it reads similar to our question in 8.1, but the big difference is there's no straight information about average or mean and standard deviation. Instead, we're given a percentage. And even though nowhere in here do we see the word proportion, we have to understand that a proportion is something that can be represented by a fraction, decimal, or percentage, right? When you're giving a portion of the population, that's the proportion, right? 18.8% is the proportion that fit this category of in this case, being overweight. So if that right there is our proportion, we're going to say officially P is the decimal form of that, 0.188, okay? Now, we need to first and foremost do our check of N, P, 1 minus P. So N being the sample size of 90, P being this decimal of 0.188, and then the complement of 0.88, 1 minus 0.88, which will end up being 0.812 if you do that subtraction. We need to see what that value will be. And we're getting 13.74. Doesn't really matter. All that matters is that it's at least 10. So since that's true, we're going to have their distribution for P hat will be normal. And that's what we needed. We needed to know that we can draw that bell-shaped curve for our distribution of P hats. Now, once we draw it, we want to remember that from the previous page and from understanding, this 18%, this 0.188, that is the center. It is centered at 0.188. If our question is for at least 19%, 19% would be to the right of 0.188, and I'll put 0.19 there, and at least would mean that or more, so we're shading to the right. So at least 19% will look like that, and now we can take that picture and convert it to z-score world. Same picture, and to find that value, we will use our new z-score formula of P hat minus P over the square root of P times 1 minus P over N. Plugging in all our numbers, P hat in question is 0.19. The value of P is 0.188. Make sure you use P down here in these calculations, so 0.188 times 0.812, and then the size of our sample was 90. I'll show you what this looks like on the calculator when I'm done, just to again make sure you're familiar with the syntax. So notice the numerator still definitely needs to be in parentheses, divided by. Now with the square root and with this formula the way it is, the square root throws in its own form or own parenthesis. You can actually just type the two numerator numbers multiplied together divided by the denominator. You can overuse parentheses if you want and put them around the numerator, but they're not necessary. They actually weren't necessary in 8.1 either when we used them there. But that value giving me 0.0486 if I round. So 0.04, actually, I apologize. I only want to take that 3. This is a z-score. 0.049, so 0.049 as the z-score for that boundary. Now we will find the area, normal CDF of 0.049, and since we're going off to the right, we'll say to 100, or 10, whichever. Normal CDF. So this part is completely the same as we saw back in 8.1, or even in chapter 7, finding the area with the z-score, getting 0.4805. Okay, and so we could say the probability that at least 19% of the 90 school-aged children aged 6 to 11 years are overweight is 0.4805. I think it's usually convenient, if possible, to phrase the proportion as a percentage and the probability that you had as an answer as a decimal. It's not required. I could have put at least 0.19. I could have put 48.05% because percentages can describe probabilities too. But it just kind of keeps the context of that's the proportion in question and that's the probability of that proportion for the sample of that size. All right, and one more here. Assume a study finds that 90% of college students with cell phones send and receive text messages with their phones. Probably higher than that at this point. If a simple random sample of 200 students with cell phones is taken, what's the probability that 164 or fewer college students send and receive text messages? All right, so this is a little different. We want to point out what's going on here. So we're definitely dealing with a known proportion, a known value for P. So P is 0.9. And we're sampling 200, so N is 200. Let's go ahead and do our check here. Our NP1 minus P is the first thing we got to figure out. 200 times 0.9, and then the component of 0.9 is 0.1, which is 18, which is at least 10, so we're good. So again, P hat is going to be known to be normally distributed. Now, from there, we are wanting to look at the information they gave us. They didn't directly state the question of P hat, notice. They gave us a number, 164, but we know that P hat, the sample proportion, if it's not given to us, it was mentioned on the previous page, can be described as the number of people or data values you want to fit a certain criteria out of the total. So to say 164 out of 200, or 0.82, that is the P hat in question. That's what this is referring to when they say 164 or fewer. They could have just as easily said 82% or fewer. Okay, so that will be our value for P hat. So as we go forward, we've got our distribution here of P hat, where we know 0.9 is the center, so 0.82 will be somewhere to its left, and we want to be that or fewer, so we're going to shade to its left, and then we will convert that over to a z-score picture, same picture, and now we will use our z-score formula. Again, P hat minus P over the square root of P times 1 minus P over N. So 0.82 was our P hat, 0.9 was our P, 0.9 times 0.1, and N is 200. And we get negative 3.771 as a z-score. Just to point out, this particular z-score is pretty unusual because we've talked about with the normal curve, -3 to +3 should be kind of your limits of what we would expect to see. So we definitely got one way out there. This question of 82% is way out there. I'll still label it. Don't want you to be confused. This boundary line is actually way over here by the tail, essentially, if we had drawn that accurately. Doesn't really matter because we can find the normal CDF to find the actual number here. So normal CDF of -10 to -3.771, as I squeeze that onto my page there. So with this value being technically so far out here in the corner, very little areas to its left. And if you type this in your calculator, just to show you here, you get that value. This is not saying the area under the curve is 8.1, right? Look to the end. We know that anything that comes out of normal CDF is supposed to be a probability between 0 and 1. So we've mentioned this in class. Notice the e to the negative 5. That's scientific notation telling you this decimal belongs 5 places to the left. So I've actually got 4 zeros in front of the 8, 1, however many places you want to go here for some accuracy, 0.0000813. And don't really have room for the sentence, but just to point out, that is the probability that 164 or fewer of the 200 students would have the sending and receiving text messages with their phones. All right. So the last page here. Let's take a look at this question again, but it's actually a different question. Same scenario, different question. So we've got 90%. We've got the simple random sample of 100 college students and 82 of them. So notice I've just changed the values basically from the 200 and 164 to 182. Really not even changing the proposed value of p hat specifically, just the way we're getting it. And what I mean by that is, same question, p is still 0.9, but now we're down to a sample size of 100. And so we're going to recheck our 0.9, actually, sorry, the n times 0.9 times 0.1. This is our check. And if we do that multiplication, we get 9. 9 is less than 10, right? That's an issue. We can't answer this question. We can't go any further with this problem because this check didn't hold. That brings us to 8.2.3c, where we say we found above that a sample of 100 wasn't enough, right? So the question is, how many more students must be sampled in order for the distribution to be approximately normal? So remember, we need this to be at least 10. Create a little equation here. N times p times 1 minus p needs to be, needs to be equal to 10, right? So what do we know? We know p. We know this value. We know that p is 0.9 and that's 0.1. But we need this to be at least 10. So we get 0.09 when you multiply those together times n equals 1. And if we divide 10 by 0.09, we get 111, and then this 0.1 repeating here. So what this tells you, notice we would need our sample size to be 111.11, but we can't sample 0.11 of a person. So what that really means is no matter what this is, you would round that up to 112. And so the official answer, how many more students must be sampled? Well, we sampled 100, so this is saying we must sample 12 more students. Right? We need 12 more than the 100 that we had originally, so that'll give us the 112 that we need to have the minimum required to meet that requirement of being at least 10.